Hi everyone. So today we're going to talk about graphing parabolas. Our notes today kind of recap what you investigated in part one of our assignment. I do want to let you know we are officially starting unit 6, which is all on graphing parabolas, getting to know the characteristics of parabolas and things like that. Just like you did on your investigation, you first graphed the parent function or the parent quadratic function, which is f of x equals x squared. It's the most basic quadratic function that we look at, and it produces the most basic parabola. And we compare all our other parabolas based on this one. Before we get started and actually writing up our notes, careful, that shouldn't be there. Before we get started actually writing up our notes, there should be a blank document of this uploaded to Google Classroom. You can download it and print it and follow along by hand. I'm actually going to be typing everything today, so you can download it and follow along in a Google Doc or in a Word document as well, and then save it so that you have the notes to look back on. But without further ado, we'll go ahead and get started. So like I said, our parent quadratic function is f of x equals x squared. Just to remind you, f of x is just another way of saying y. So if I had y equals x squared, still the parent function. We've talked about quadratics, and in order for a function to be a quadratic, the largest exponent has to be 2. So if you have x squared, another variable squared, as long as the largest variable is being raised to the second power, as long as the largest exponent of the variable is to the second power, then it's considered to be a quadratic function. And we've talked about how quadratic functions form parabolas. Back in unit 5, we factored quadratic functions to solve for x-intercepts of parabolas. That's what we were doing. And we're going to look at that in more detail later on in this unit. But we can see here we have a parabola. A parabola is a U-shaped curve that's the graph for any quadratic function or quadratic equation. Parabolas are a little bit different than linear functions because if you notice here, parabolas change direction. So if we read this from left to right, I can see that as x gets closer to 0, so in other words, when x is negative, this parabola is decreasing. Then I get to this point, which we'll talk about in a minute, the vertex, and I can see that it makes the parabola change direction. So this vertex is the point where the parabola changes direction. So when x is greater than 0, right, when x is positive, I can see that my parabola is actually increasing. So this is very different compared to our linear functions. If you remember, our linear functions, I can draw a line on here for you, right? I have either positive lines, I could have a negative line, I could have a flat line, which has a 0 slope, or I can have a vertical line, which has no slope. It's undefined, right? So lines, and I know this is a rough sketch, but if you notice here, our lines are different because they don't change directions. Whereas our parabola, our U-shaped curve, does change direction. So this makes these two types of functions very different. So let's actually go ahead and define what a parabola is. We've talked about it, we've looked at their graphs before, but formally it's considered to be the U-shaped curve the U-shaped curve graph of a quadratic function. And if you take a look here, let me scroll so you can see a little bit. Here we have our vertex. So like I said, parabolas change direction. I can see here when x, so I'm looking at my x-axis, when x is less than 0, in other words, when I'm over here, I'm dealing with negatives, my parabola is decreasing. When I hit the vertex, it changes direction, and when x is greater than 0, when I'm looking at positive x values, my parabola is increasing. So the vertex is actually the point where the graph, or we can say the graph slash parabola, changes direction. And right now we can see that with this parabola, the vertex is actually the lowest point. So let's add that in there. Let's say it can be the vertex is either the lowest point on the parabola. Actually, let's say the vertex is either the lowest or highest point on the parabola. So if we take a look at this parabola here, right, this parabola is opening up, which shows us that this vertex is the lowest point on the parabola. So when it's the lowest point, we actually call that the minimum point. And later on in the unit, we'll look at parabolas that open down. And if you kind of think of like a hill or a mountain, when you get to that peak, that's your highest point, also known as the maximum, or also known as the vertex. When it's the highest point, we consider it a maximum. We'll get into that a little bit more later on, but I just wanted to point out, because parabolas change direction, they either have a lowest point, a minimum, or a highest point, a maximum, which we'll talk about in more detail. Now, also unlike linear functions, parabolas are symmetric. So if you think back to like symmetry when you were a kid, right? So if you think back to when it was Valentine's Day and you were a kid and you were making Valentines, oftentimes we would take like a piece of construction paper, fold it in half, and then we would draw half a heart, cut that half out, unfold it, and we would get a perfectly symmetrical heart. And that's kind of what's going on with our parabolas here. We can see that the parabola, that this left-hand side, if I were to reflect it over the y-axis or over the what we call the axis of symmetry, this dotted line, it would end up laying flat on the right side. So all parabolas are, symmetrical through a vertical line. So the axis of symmetry, let's go ahead and define that piece, is the vertical line. So the axis of symmetry is the vertical line that divides a parabola into two symmetrical my word is hiding, one second. Symmetrical parts. And let me actually come in and maybe underline these so they're a little bit stand out as the vocab words. Okay, so going back to this axis of symmetry, right? So if we take a look, our axis of symmetry is always a vertical line. And we talked about how vertical lines can be written as an x equals equation. So we can actually find the equation for our axis of symmetry. In this situation, this one's kind of interesting with the parent function. It's actually symmetrical over the y-axis. But since this is a vertical line, it can be written of the form x equals some number. So let's actually add that in. So since the axis of symmetry is a vertical line, the equation can be written in the form of x equals some number, whatever that number is on the x-axis. Now, for our parent function, we can see that the axis of symmetry is the y-axis. However, we could also say that the axis of symmetry is when x is 0. So we're going to say for the parent quadratic function, the axis of symmetry is x equals 0, also known as the y, running out of space here, y axis. Okay. Having some formatting issues. Give me a second here. Things are not moving the way they're supposed to. if you print this out, it really only is a page, but as I write into it, it starts, you know how things start moving. I can actually take some of this space back. Okay, anyway, that's good enough. Okay, so those are the different characteristics when we're dealing with a parabola. So we have the fact that it's called a parabola, the vertex, the axis of symmetry. Because it changes directions, it decreases and increases in different increments. And we'll kind of talk about that in more detail in the next few graphs. So our parabolas, which this piece you probably looked at, or you did look at rather, in the investigation. So with our parabolas, they can open wider or narrower, and we'll talk about which happens when. So this a in front of the x squared, that leading coefficient of a, is going to determine how wide or how narrow our parabola opens. So if we look at this, it's saying when when a is between 0 and 1. So if you think about it, if you think about numbers on the number line between 0 and 1, in other words, we're talking about when a is a fraction. So when the leading coefficient of x squared, when a is a fraction, we're looking at a vertical shrink of the graph of f of x equals x squared. So what does that mean? That means that if we compare our parent function, our original, which is our blue graph here, when a is a fraction, it's a vertical shrink, meaning that it's getting wider. And this language, vertical shrink, can sometimes be confusing to kids or students or even anybody learning about quadratics, right? So you're like, if it's getting wider, why is it shrinking? The way that I like to think of this is, imagine that you were pushing down, right, on this blue graph. If you're applying force onto this blue graph, it would force the pressure that you're applying onto that blue graph would, like pushing down on it, would cause it to open, to vertically shrink, to open wider. So in other words, and something that we can kind of write in to help us here, a vertical shrink really means, let me see if I have enough space here. A vertical shrink, we can think of that as growing slower, which as a result is getting wider. So in this case, the vertical shrink means that it's getting wider. And if we compare our original, our parent function in the blue, with our fractional coefficient of x squared, when a is a fraction, we can see that red graph is getting wider. Okay, and then here, when a is greater than 1, we can call it a vertical stretch of our parent function x squared. So again, we're comparing the blue, we're comparing our original, the blue graph, and when a is greater than 1, when our leading coefficient is larger than 1, it's a vertical stretch of our parent function. In other words, when a is greater than 1, the graph is getting skinnier, it's getting narrower. So if you look, our blue is our standard, our parent function, and when we compare it to green, we can see that the green function is much skinnier, much narrower. So again, this language of a vertical stretch is kind of weird. You're like, well, how's it stretching if it's getting narrower? Think about like if you're, and this is kind of a weird example, but think about like if you were to pull our parent function, right? If you were to take like these arrows and kind of pull them up, think about like if you're stretching in bed, you get like really, 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 really long, you're growing vertically. And that's what's happening here with our graph. If you took these blue arrows here and you pulled them up, that would end up stretching your parabola, making it skinnier and taller. So let's actually, to kind of help us with that language, let's write in a little bit of notes as well. So a vertical stretch, we can consider the parabola to be growing faster as a result it's getting, this is kind of weird to say, it's getting narrower. It's getting, you can even think of it as like skinnier, if that helps. So the number in front of x squares determines the width, how wide or how narrow our parabola opens. That was like the first part of your investigation. Then the second part of your investigation dealt with this constant, this plus c at the end. And hopefully from your discoveries, you were able to see that when the constant is greater than 0, your parabola moves up. So again, here's our blue. Our blue is representing our parent function. And here we're looking at when ax squared plus c, when c is greater than 0. So we're looking at the green. So when we compare our parent function, which doesn't have plus c, it's just ax squared, and then we add a positive number, that means that this parabola is shifting up. A vertical translation just means a shift up or down. And so let's actually add that in as well. A vertical translation means a shift up or down. Now you have to be able to determine when it's going to go up or down. Oops. Okay. So if we look at our red graph here, so when we have, and this should be minus, oh sorry, no, plus, because we'll deal with the absolute value here. So here we have when c is less than 0. So think about it, if c is negative, and that's why I switched it to be minus here, but let me talk about why that is. So if c is negative, adding a negative is the same as just subtracting, right? So if this is either subtracting c or you're adding a negative c, if c is negative, that means that the parabola is shifting down that many units. Let's talk about this absolute value here. You can't actually move negative units, right? Let's say that c here was -2. You can't actually move -2 units. The negative refers to the direction. So you're still moving a +2 units, but to show that you're moving negative, you're actually going down. So that's why we talk about the absolute value, because you can't move a negative distance. So when c is a negative number, less than 0, this graph is going to move down however many c units. So if we look here, our parent function starts at the origin, right? And in comparison, this red function, when you're adding a negative, ends up moving it down. So here, it's just showing you, kind of referring back to the vertex, talking about the axis of symmetry. So this says the vertex of the graph f of x equals ax squared plus c is going to be 0, c. So what that means is the ordered pair here, right, in the green one is 0 because we're on the y-axis, x is 0, and then a positive c since we moved up. Here it's 0 again because we're on the y-axis and x is 0, and then negative c because again we moved down. And since all of these parabolas are symmetrical over the y-axis, the axis of symmetry is x equals 0, also known as the y-axis. Okay, let's take a look at some of these graphs here to talk about the characteristics. And I'm just trying to save some space here. We might end up going on the next page, and that's okay. Okay, we're good. So for exercises 1 and 2, we want to identify the characteristics of the quadratic function and its graph. So what that means is we want to identify the vertex, we want to identify the axis of symmetry. I do want to talk about domain and range. We haven't yet, but we've talked about it in previous units. We did a graded assignment, a few graded assignments on domain and range. I also want to talk about when it's increasing and decreasing. So those are the three, vertex, axis of symmetry, domain, range, increasing, decreasing. So that's like 6 things I want to mention about each graph. So for this one, right, we'll start with the vertex. For this one, the vertex as an ordered pair, that's going to be where the parabola changes direction. So I can see from here, it's as I read this from left to right, it's decreasing, 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 levels out. Here's my vertex. So that point would be -1, +1. Whoops, number here is killing me. Okay, let's get rid of that. Sorry, Word is giving me all kinds of formatting issues. All right, so there's the vertex. Now I want to talk about the axis of symmetry. So that's going to be the vertical line that the parabola is symmetric over. And let me see if I can even go ahead and insert a picture. Here we go. So I can see that my axis of symmetry always contains my vertex point, because the vertex is the point where it's changing direction. So the axis of symmetry is going to always contain that vertex point. So there's my blue axis of symmetry. Let me make it red so it stands out more. Sorry, just trying to make it more obvious for you. Okay, there's my axis of symmetry, right? It's a vertical line, so it's going to be of the form x equals. And now we just have to figure out, well, what's the x value of my line? And if I notice, since my vertex is on the axis of symmetry, it's always going to be the x value of my vertex. So the axis of symmetry is x equals -1. Okay, the next thing I wanted to talk about was the domain. If you remember, the domain is all the x values. So if you take a look at our parabola here, what's happening is as this parabola opens up, it's getting wider and wider and wider and wider, right? It's getting wider over here and wider on this side, which means it's going to reach all of the x values, making the domain all real numbers. Just continue here so we can see the graph. Now the range is all the y values. So here we're talking about the y values. Now, because parabolas change direction, the range is not going to be all real numbers. If you think about this graph is opening up, and the lowest point on the graph here is at the vertex. This parabola will never hit 0, -1, -5. It's never going to hit any y values less than -1. Sorry, less than +1 right here. We're on the y-axis. It's never going to hit 0. It's never going to hit -1, -2, nothing down here. But we can see that it's going to forever, right? I'm going to always hit everything above +1, right? Because we can see this parabola is going up. Therefore, we can say that the range here, since it's the y values, y is greater than or equal to +1. Now, let's talk about when the graph is decreasing, excuse me. So here I can see, remember, you read graphs from left to right. So as I'm reading this from left to right, I'm seeing it's decreasing, 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 vertex, increasing, 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 increasing. So if I just want to deal with the decreasing side, I'm over here, right? And I want to talk about the x values when this parabola is decreasing. So I can see that when x is negative, right, I'm looking at my x-axis, when x is negative up until we get to -1, this graph is decreasing. So we can say that the graph decreases when x is less than -1. We don't want to include -1 because at the vertex, it's neither increasing nor decreasing. That's the point where it changes direction. So you can almost think of that as like a neutral point. Now let's talk about when it's increasing. So again, when we read this from left to right, this was decreasing, 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 vertex, neither increasing nor decreasing. then increasing, 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 increasing forever, right? So again, we're looking at the x values when this graph is increasing. So I can see that the vertex is where it starts to change direction. So when x is -1, it's neutral, but anything greater, anything more than -1 on the x is showing this parabola increasing. So this increasing piece would actually be when x is greater than -1. And if you notice, a lot of these pieces of information are kind of depending on the vertex, right? Our axis of symmetry is the x coordinate of our vertex. Our range, in this situation, our y value of our vertex comes up in our range. When we're trying to find whether the graph is increasing or decreasing, we're looking at the x values before and after the x value of the vertex. So the vertex does play a big role here. This is number 2. I had to delete the number because it was a formatting nightmare. But anyway, you can continue, calling it number 2 on your worksheet, or if you printed it out, that works as well. So we're going to do the same thing here. We're going to look at the vertex. Again, that's the point where the parabola changes direction. In this situation, since this parabola is opening up, I can see, and by the way, the parabola we're comparing here is this blue one. So that's kind of like what we're looking at. If you notice, this blue graph is g of x equals 2x squared, and this parent function f of x equals x squared. Here, this blue graph is skinnier, right? It's narrower, also known as a vertical stretch, because a is greater than 1, which we talked about above. And it's kind of opposite. Let's actually go back to that for a second. It's opposite of what you would think. So if a is a fraction, it's actually getting wider. And if a is greater than 1, it's getting narrower. A lot of students think a fraction should get smaller and a whole number should get wider. It's the reverse of what you would normally think. A fractional coefficient is going to make a wider parabola, whereas a coefficient greater than 1 is going to make a narrower parabola. So let's go back here. That's why this function g of x equals 2x squared, the coefficient of x squared, 2, is greater than 1, making a skinnier, also known as narrower parabola. Okay, so our vertex in this situation, they both happen to be at the origin, which is 0, 0. Our axis of symmetry here, and I'm running out of space, so we'll call it like that. Our axis of symmetry is the y-axis. So you could write the y-axis, but we want to use equations of lines. It ends up being x equals 0. Our domain here, and like we mentioned, the domain is all the x values. The domain, what's happening, just like in this parabola, and you'll start to notice in pretty much all of your parabolas, if they're opening up, up or down, which we'll talk about down later on, but in all of our parabolas, as this opens up, I can see that it's getting wider and wider and wider, meaning it's going to hit all my negative x's, all my positive x's, meaning my domain is all real numbers. Do I have enough space here? I could put the abbreviation as well, the symbol. Give me a second. Let me see if I can find it. I don't see it on my math type. However, we've kind of drawn the domain, the symbol before. It's that R with the extra line in it. Oops. Sorry guys, the formatting on Word is just making this more difficult. All right, let's talk about the range. So here, this is for our second one. The range, again, is the y values. The y values depend on the vertex. When our parabola opens up, our vertex is the lowest point. So I can see here that my vertex is 0, 0. This graph is never going to go below 0 in the y values. It's never going to hit -1. It's never going to hit -10, -100. But I can see it's going to hit all my positive values because it's opening up. So therefore, we can say the range is y is greater than or equal to 0. Now for when it's increasing or decreasing. Let's start with decreasing. So as we read this from left to right, I can see this graph is decreasing, 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 vertex, changes direction, increasing, 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 increasing. So my decreasing piece was over here, right? So I can see here when it's decreasing, x is all my negative numbers, right? So when x is negative, in other words, when it's negative and approaching 0, it's decreasing. In other words, when x is less than 0, the graph is decreasing, right? Numbers approaching 0 or negative numbers would be when x is less than 0. Now looking at our increasing. So when is this graph increasing? Okay, so we said it was decreasing on this side until we got to the vertex. And now looking when it's increasing, right, is past the vertex. So I can see it's increasing when x is positive. In other words, when x is greater than 0, when x is getting larger than 0, it's becoming more positive, it would be increasing. So we can say the increment or the part of the graph where it's increasing is when x is greater than, there we go, greater than 0. Okay, so once you've watched the notes, what you want to do, obviously save your work if you've written a Word document or a Google form, but there's actually an assignment on the new Big Ideas platform that you want to take a look at. So remember, you're going to go to demo.bigideas.com. We'll put a link on there for you. Log in with the username and password that you created either Thursday, Friday, or over the weekend. It was the one you recently created. You cannot access this through Clever, so you want to make sure you're going to demo.bigideasmath.com. We'll put the link up for you. And then you're going to use your username and password that you created. And then you'll see that there's an assignment. It's about 8 problems highlighting all these different characteristics that we talked about, that you investigated in part 1 and that we talked about in today's notes. As always, if you have any questions, feel free to reach out to your teacher. You can email us, message us on Google Hangout. We'll set up a time for Google Meet. Good luck, and if you have any questions, let us know.